Okay, so in Newton's law, practice problem number 14, we have two masses, M1 and M2, and they're connected by a string here, okay, of negligible mass that passes over a pulley. And the block with mass M2, so I've labeled that as block 2, is on a ramp with an inclination of 30 degrees, as shown. And there's no friction force. We're saying there's no friction force between block 2 and the ramp. So negligible or very close to zero friction force. First thing we're asked to do is to draw a free body diagram for each block, and then represent that with Newton's second law, or Newton's law of F equals ma. So the first thing you want to think about is your reference frame here. So I like to, if there's something on an incline, I like to make my reference frame, and this is good practice. This is a good practice to make the parallel to the incline your positive, your x direction, and perpendicular to that incline your y direction. Okay, that'll just make things easier on you, because if this block is accelerating, it's going to be accelerating in this x direction. Okay. So constructing a free body diagram, let's start out with our free body diagram for mass 2. Okay, so here we have mass 2. I'll label that right there, mass 2. Okay, so we have a force of gravity, and force of gravity always acts straight down, right? It's a terrible straight line. See if we can get it straight down. That's about as good as it's probably going to get. So we have force of gravity for block 2 acting straight downward. We have a normal force acting on block 2. Normal force. And that is going to always act perpendicular to the contacting surfaces. Okay, and we have a tension force acting on block 2. Okay, and we can call that force of tension. You can label tension force with Ft or with T. Okay, so that is our free body diagram for 2. Okay, what we're going to want to end up doing is splitting up this force of gravity into its components that are parallel and perpendicular to the incline. Okay, so we will end up solving for FG2Y, FG2Y, and FG2X. Okay, those will be important, but your free body diagram is actually complete with those arrows that I drew in yellow. Okay, for our second, so this is, we're working on part A right now. So for our second free body diagram of mass 1, a little simpler this one. There's no surface that it's in contact, so we just have the force of tension up. Okay, and there's the center of mass of our block, and we have the force of gravity acting on block 1. Okay, so we've drawn our free body diagrams. Now we want to write Newton's second law for these. Okay, so let's start out with block 1, since it's fairly simple here. So we want to establish a reference frame. So let's call downward. Let's make the assumption that it accelerates downward, and we can call downward the positive direction. Okay, so let's call downward the positive direction, and we would say the sum of the forces in this y direction equals the mass of 1 times acceleration in this y direction. So we have, if the positive is downward, we have Fg1 as our first force minus Ft equals M1A. Okay, so these are connected like we've seen in previous problems. So A2, the acceleration of, if these do accelerate, the acceleration of block 2 is going to equal the acceleration of block 1, which is just going to equal, we'll say, A. Okay, because they're connected by a rope and tension, they're going to move as one unit. Okay, or as one system. Okay, so here we have, this is really all we need to do for the mathematical representation for the free body diagram for block 1, because we just have forces acting along that y direction. So we're done with that one. Okay, but let's look at block 2. So block 2, we have our, remember we called this our x direction and perpendicular to the incline our y direction. So we have 2 dimensions that we have forces acting in. So we can sum the forces in the x direction, and those will equal mass of 2 times A2, which we said is just going to be A. So let's draw that out. We said our positive x direction is up the incline or to the right. So we have force of tension minus F2, or F, I labeled it FG2. So the weight of block 2 in the x direction. Okay, that's going to equal M2A. Okay, and if you recall from other examples, if we know that this angle right here is 30 degrees, that means this angle right here would be 30. And that means that F2, the force of gravity in the x direction is gonna be the sine of that angle. So we have FG2 sine of 30 is going to be our FG2x. Okay, so we can rewrite this as FT minus FG2 sine 30 equals M2A. And there we have our sum of the forces in the x direction for block 2. But we still need to do the sum of the forces in our y direction. And in the y direction, we are saying in this system, our block is not going to be accelerated. It's going to stay on this ramp. So we're not going to have any acceleration in the y direction. It's not going to go up off the ramp, and it's not going to sink down into the ramp. So we know our acceleration in the y is going to be 0. So the sum of the forces in our y direction here, so Fn, the normal force, minus Fg2y is going to equal 0. Okay, similar to what we did with our Fg2x, we want to solve for our Fg2y in terms of Fg2. So we have force normal minus Fg2 times the cosine of 30 is going to equal 0. Okay, so there are our free body diagrams. And then for block 2, we have 2 equations to represent those free body diagrams. And for block 1, we just have the one equation, okay, because there's no x motion for block 1. Okay, so that wraps up part A. Okay, part B, the net force on each block is 0. Okay, calculate the mass of M1 in terms of the mass M2. Okay, so we wrote our equations saying that, okay, well, maybe we're going to have some acceleration in this x direction. We called that A. But if the sum of the forces on the net force on each block is 0, that means it's kind of like a Newton's first law equation where the sum of the forces equals 0. So this creates an equation. So this is now we're working on part B. Actually, let me change colors just so we can kind of differentiate here. So part B, we now know that our sum of our forces, Fg2 sine 30 equals 0. And we also have our other equations as well. We have Fg1 minus Ft equals 0, and we already had this equation written down where it equals 0. Okay, so looking at those 3 equations, we want, in the question it gives us, we want the mass M1 in terms of M2. Okay, so we probably want to rewrite our force of gravity using the masses of the blocks. Okay, and additionally, we probably want to get rid of that tension force. So it might be a good idea to substitute out that tension force. So we're just dealing with the masses and can relate the masses to each other. Okay, so this equation right here, actually, if I substitute in m1g for force of gravity, which remember F equals ma, and for the weight of an object, that's going to be equal to m times little g to determine the weight of an object. Okay, and we're assuming that this is happening on Earth. Okay, so we use little g. So we can easily substitute m1g in for force of tension. Okay, when the situation is that there's no net force. Okay, so for this situation, when there's no net force, we know that m1g minus m2g sine 30 equals 0. Okay, well, can do a couple things here. I can add this term m2g to both sides, m2g sine 30. So I get this relationship, and my g is going to cancel out. Okay, so I get that m1 equals 1/2 of m2. Okay, because sine of 30 is a half. Okay, so there is my relationship. This was what the problem was asking for. Determine the mass of m1 in terms of m2. So we have that m1 equals 1/2 m2. Okay, so in C, now we have the inclination of the ramp reduced to 20 degrees, and block 2 is released from rest. Okay, so we knew that at 30 degrees, this was a static situation, nothing was moving. Okay, but as soon as you reduce this, this component of gravity pulling this block 2 back down is going to decrease. Okay, it's going to decrease, and if that decreases, and you don't change the mass of m1, then you're going to the system is going to accelerate, and mass 1 is going to fall down to the ground, and mass 2 is going to come up the incline. Okay, so in C, we're asked to determine the time dependence of block m2. What if the string remains taut, so if the system accelerates together. So what we want to do is we want to use Newton's second law to find that acceleration, and then we can use that acceleration to find our time dependence of the displacement. That's just a fancy way to say we want to use our x equals x naught plus v naught t plus 1/2 at squared. Oh, v naught t plus 1/2 at squared equation. Okay, so that's just a fancy way to say, and then plug in your acceleration to our motion equations, or one of our motion equation from last unit. Okay, so let's go ahead and give this a try. So in part C, if we let's draw this system. So we have a pulley system, but let's just draw it like mass 1. We know mass 2 and mass 1 are connected. In this new system, okay, we have a 20-degree angle now. Okay, and then, here's our pulley, here's our mass 2, here's our mass 1, 2, 1. So we can think about this system as a whole. If there's no friction, we have the force of gravity, so m2g sine 20, acting in a way that it's kind of pulling block 2 down the ramp. Okay, But we know that this is going to accelerate in this direction because at 30 degrees, it was a static situation. So m2g sine 20 is going to be is less than m2g sine 30. So we know that this force of gravity, so m1g, is going to kind of overtake, and this whole system is going to move so that 1 is falling down and 2 is coming up the incline. Okay, so we know our acceleration is going to be in this direction. So this is a little different, but hopefully you can see that I've kind of just kind of turned this pulley system into, they're connected by a rope, so we can kind of treat them as one system here. Okay, so M1G, and the way we've set up our reference frame, remember we said that this was the positive X, and this was our like positive Y, was downward. I'll add my little plus signs to those. So let's write Newton's laws for this whole system. So we have the sum of the forces equals m1 plus m2 times this acceleration. Okay, we have m2g sine 20, which is going to be a negative m2g sine 20 plus m1g. Okay, remember it's negative because we've called to the right positive, and that's the direction of the acceleration. So this is going to, the m1g is our positive value, and the m2g sine 20 is our negative value. And all of this is going to equal m1 plus m2 times the acceleration. Okay. So right now this looks kind of messy, but we do know that m1 equals 1/2 m2. So that is likely going to be helpful here in solving for an actual value of the acceleration. So let's rearrange this a little bit, and then let's see if we plug in 1/2 m2 everywhere we have m1, see if that helps us at all. Okay, so I can rearrange this so I solve for A, and I'm actually going to move the m2g sine 20 so that I feel like out here I might forget that negative sign. And then we're going to divide by m1 plus m2, and that is going to equal A. Okay. So I can pull out a g, but that's about all I can do right now. So let's do that. Let's pull out the g out to the front. m1 minus m2 g sine 20 divided by m1 plus m2. And that all equals A. So here we're at a point where this m1 equals 1/2 m2 up here might become useful. Let's go ahead and plug that in. So we have g, and then we'll do 1/2 m2 minus, oops, y'all, I forgot to take my g out. Remember I pulled the g out front. Okay, so m2 sine 20 divided by 1/2 m2 plus m2, and all that is going to equal A. Okay, well, this is looking actually kind of promising. So let's go ahead and pull this m2 from each of these terms out front. So we have gm2 times 1/2 minus sine of 20. Okay, well, that's good. This is just a number. 1/2 sine of 20 is just a number. And then if we add 1/2 m2 plus m2, that's like 1/2 m2 plus 2/2 m2. So we get 3/2 m2. Check this out. The m2 cancels. So now we have that the acceleration is going to equal g times 1/2 minus sine of 20 over 2, or over 3/2. Okay, and that just becomes a number. Okay, so we have, well, we can rewrite this as A equals g times 0.5 minus sine 20 divided by 3/2 is just 1.5. So that's what we plug into our calculator, and we end up getting that A equals like 0. That's a 0, not a 6. 0.10532 g. Okay, so here's our acceleration, and that is part of our process of finding our answer, but what we actually want is the time dependence of the displacement. So remember, we wanted to end up plugging in our acceleration to this equation here. Oh, there comes the work. Okay, so we have our equation that x equals x naught plus v naught xt plus 1/2 at squared. Okay, and we're calling our x direction. Remember, we made this like, so our positive x direction is going to be in the same direction that we called our acceleration positive, which is in reality like this direction, right? Over the pulley and down. So we're going to call basically this position where it's released from rest. Mass 2 is released from rest. We'll call that 0, and because it's released from 0, we know that its initial velocity is 0 meters per second. So now we can plug x equals, well, this is 0, this is 0. So x equals 1/2 times our acceleration we saw, 4.10532 g times t squared. Okay, and if we multiply 1/2 times 0.10532 g, we get 0.516 t squared. Okay, equals x. So there is our time dependence, and I could have flipped it around. X equals 0.156 t squared, but it was just kind of written out, and so I put the equals x on the other side, which works as well. Okay, so there's our equation for the time dependence of the position of the blocks, or block 2. That one was kind of a doozy. So D was kind of long, or C was pretty long. We had to figure out the acceleration first, which was a process in itself, and then we could plug it in, that acceleration, we could plug it into our motion equation.